This is a video on our VR work. I have two other videos posted to YouTube. Those are concerned with model selection, and this one is concerned with our most recent work in outlier cleaning, using virtual reality to do the outlier cleaning in conjunction with computations of massive amounts of outlier similarity measures. The outlier cleaning we're focusing on is for quantitative analysis versus, for example, classification. And in quantitative analysis, in analytical chemistry, what we do typically is build a model for the analyte of interest, perhaps iron, how much iron is in your blood. And so this model allows you then to predict the analyte in new samples. So to start with, you start with a training set or a calibration set. Typically we use spectra. So the rows are near IR or IR spectra, and fluorescence spectra, UV vis, etc. So every row is a different sample. And every sample in row in this X has a corresponding row in this column vector of our reference values, how much that analyte is in. That's our quantitative information. We build a model typically with PLS, and then we can just, with this model, we can interproduct that with a new target sample spectrum, and we can get an estimate of the analyte amount. So if we don't outlier clean the training set, that can change the model direction. It's a vector, model direction and magnitude. And so then when we go to use it, it's not quite in the right magnitude or pointing in the right direction. It got biased by the outliers. And so we don't predict the new samples very well. Two issues we have to contend with in outlier cleaning are swamping and masking. Regardless of which one is occurring, when you have an autonomous machine learning algorithm to do your outlier cleaning, you have to set thresholds. And then if the sample is above this threshold, if you're minimizing the similarity measure with its corresponding threshold, then it's removed. And if it's below the threshold, it's kept. And that can cause problems. You can artificially throw out normals as well as artificially keep outliers in your data set, and then you have fully removed all your outliers. So the VR will hopefully direct us in the right direction of when to decide if a sample is an outlier or not, regardless of our similarity threshold that would normally have been applied. We need to represent our samples in virtual reality. And when you have an object placed in virtual reality, it's called a glyph because it has some kind of shape to it. Usually it'll have texture and color and size and so forth. And we're going to use these prism values we developed. And these prism values were originally developed as a quantitative z-score for a sample, and to talk about for a new target sample, the model generalizability to that target sample or the prediction reliability of a sample from the training set, as well as any new target samples. And in developing this quantitative z-score, we use these prism X values, hundreds of spectral similarities because we have our spectra. And then we have these prism Y values, and these are values based, I say, estimated analyte amounts because this was originally developed for using unlabeled data. Now for outlier cleaning, we have also the training set are labeled with the analyte reference values because we're going to build a model with them. And so we also include in this case, we include in the prism Y values Y similarities based off studentized T residual as a similarity measure. Anyways, we composite them all and we have we can get a final z-score for every sample. Here's a picture of the glyph we'll see in the VR. For this one, it's a prism X glyph, and the size is the z-score for the sample, and then the spikes in this case are 316 sample-wise differences on our similarity values we're using for prism X value. So you can see a lot of these spikes are kind of close to the surface, and like you'll see in the video, this sample, the spikes are pretty big. So the bigger the spikes, the more dissimilar the sample is relative to the other samples, and then obviously the bigger the z-score too. Here are the prism Y glyphs. And then here are the composite glyphs of our prism values from the X and Y. And when you touch a glyph, you get the sample number, and then you get the z-score, as you'll see in the video. The way we run the process is we're going to use shape, position, and z-score, especially at first, if there's super big z values, and then later, not so much of the z-score, but more just the shape and position of the samples relative to the rest of the training set. So if there's an outlier, we just remove the one outlier, and then we recalculate the whole PCA and all the prism values again, and then all the new prism X, Y, and composite glyphs are thrown into VR, and we can explore them and decide if there's another outlier or not. And then we stop, like I said, when it appears no samples are outliers, in spite of the z-scores. So again, it's towards the end, it's all about what it looks like and position, not so much the z-score value. The data set we're going to work with, we picked this one because the original paper identified one sample as an outlier, and that was based off high leverage values. So that would be like a prism. That's one of our Prism X outlier similarity measures, but it's not the only one because, like I said, we have 316. And then it also identified the sample as a Y outlier because it had a large studentized residual. And that was the only sample identified as outlier. So we're going to see if through the prism we can actually identify more and perhaps end up doing more. So what we do is, to see how well we're doing, we do 100 cross vals with a 60-40 split, 60% of the training sample of the original training set going to the training set to build the model, and 40% going to the validation set. So we get the prediction error on the validation set across our PLS latent variables, and then we're just going to plot the mean of those across all 100 cross-val splits. So we're going to do that before we do any outlier cleaning, and then every time we remove a sample, we're going to do the 100 cross-vals to get a prediction set of prediction errors to see how we're doing. That we, hopefully, if we keep removing outliers, we should keep dropping the error. This is the video of the VR, so we'll watch it now. So Hiram is the student, and he's just going to show at first, here's our Prism X glyphs. All three data clouds are in the VR. You can go to either one anytime you want. And they're the Prism Y glyphs, and then the composite glyphs. So now he'll go back to the Prism X glyphs, and he's going to zoom in just to show you a little bit with the VR. You can move the samples around, and we can click a button and put everybody back to their original PCA coordinates, which I think is what just happened there. But you can zoom in, and in VR, it's very nice. You can walk through your data cloud and look around, look up, down, and so forth, which we find very handy. And as well as you can grab any one of those glyphs and hold it in your hand and move it around. And we're developing with our haptic gloves so that you can actually feel the glyphs and the spikes. Okay, so there's sample 1. There's sample 115, the big hairy one, very big z-score. And then we're going to look at those samples in the Y. And I think the sample 115 is not, or the Z's, the Y's, yeah. There's not much of an outlier. There's some bigger ones there. It's only a 3. But the composite, because of the Prism X values, is quite big. So we're going to remove that sample first. So Hiram just throws it out there. It's gone. So now it's going to recalculate. So this is what it all looks like with sample 115 removed. And now you can see sample 1 z-score has gone up because sample 115 was the biggest, and it was causing sample 1 to be smaller. And now we're just going to look at them all. So you got to remember, this is a 2D flat screen view of a 3D world. So it looks much, much different in the, it's much more impressive when you actually see the VR. So sample 1 is our next outlier, and we ended up removing 7 more outliers. So a total of 9 outliers were removed from the 115. And this is the view after all 9 were removed. So you can see there's some samples with some bigger z-scores, but they're kind of part of a cluster and they all kind of all the same. So we're going to call that good. Some people would say there's no such thing as outliers. You just don't have enough samples. But for me, when you have obvious outliers like that first one, 115, clearly you should be removing them. These, maybe some, in terms of a threshold, they probably would have gotten removed as outliers, further decimating your training set. But for me, it just looks like, they don't look like outliers. They're bigger Z's, but the way they're clustered up, there's more than one. It just looks like part of the covariance structure of the training set. This is what we saw. This was the initial set of glyphs. This was what you saw in the VR movie after the first sample was removed, number 115. And then this was what you saw in the VR movie after 9 samples were removed from the 115. So quite a bit of difference definitely between doing nothing and removing 9. Even after removing 1, there's quite a bit of difference in the landscape of the data cloud. Here are the prediction errors from doing our cross valves. So the blue line is the initial. We didn't do anything. That's, those are the prediction errors. The red is after sample 115 was removed, which is the same sample that the original paper removed from using an autonomous algorithm. But then they removed no more. And part of the problem is we still kept removing, even if we were using z-values in an autonomous way, we would have kept removing. But we probably would have gone too far though, but we would have removed these 9 samples. Because we have so many looks at the data, just look using a high leverage and a high student residuals, 2 outlier views is probably not enough to get the global view of whether a sample truly is an outlier. This is like a very local micro view. And with our prism, we get a more global macroscopic view of what's going on. And once we removed all our outliers, our prediction error is quite good. And if we actually keep removing outliers, the curve here really doesn't, it infinitesimally may drop or might infinitesimally go up, further indicating that there's really no need to remove any more samples. That concludes our VR video on outlier cleaning, and we have lots of different data sets, and like it says there, we're in the process of preparing a manuscript for Journal of Chemometrics.